Hello everyone, we're going to talk about the ratio test today. The first thing we need to talk about are absolute values, and I just want to remind you that absolute values behave very nicely with respect to multiplication and division. So the absolute value of the product is the product of the absolute values, and the absolute value of the quotient is the quotient of the absolute values. Now we can also talk about powers. So a power, the absolute value of a power, is really just the absolute value of a big old product, right? And that's a big old product of absolute values, which is that absolute value raised to the power. So when we look at this first part here, it's equal to this last part. And basically you can think of this as just meaning that this power that's inside an absolute value can get moved outside of it. Okay, so here's a series we don't know how to analyze yet. The numerator is an n squared, which reminds us of the p series. The denominator is a 2 to the n, which reminds us of geometric series. So this series has elements of both geometric series and p series, so it's neither one. Today we'll learn how to tell whether this series converges or diverges. Okay, so let's consider this series, whose terms are absolute value of a to the n, and we'll look at the limit as n goes to infinity of this ratio of the n plus 1 term over the n term in absolute values, and let's say that limit is r. Now if the limit is r, then eventually these terms must get very close to r, right? So they'll be approximately equal to r eventually. And we can rewrite these terms using our absolute value rules as, instead of the absolute value of the quotient of the absolute values. And now this really starts to remind us of a geometric series phenomenon. With a geometric series, this ratio would always equal r, but here we're saying this ratio usually equals r, or is approximately equal to r. So we can think of this r as an approximate common ratio. So if that r is an approximate common ratio, then that means this series is approximately a geometric series. If you'll remember about geometric series, they converge if the common ratio is between -1 and 1. Now, this approximate common ratio can't ever be negative since absolute values are never negative. So the only thing that should really matter is if this approximate common ratio is less than 1. And indeed, if that approximate common ratio is less than 1, then this approximate geometric series converges. So by the absolute convergence test, since the series with absolute values converges, we can conclude that the series without absolute values converges as well. Okay, so what if that approximate common ratio r is bigger than 1? Well, since these ratios are approximately equal to r, we can multiply both sides of this approximation by the denominator to get that this absolute value an plus 1 is equal to r times absolute value an. But now since this number is bigger than 1, this is going to be bigger than this, all right? So the absolute value an plus 1 is larger than absolute value an, which means that these terms, these absolute value an terms, are increasing, and that means they cannot converge to 0 if they're getting bigger and bigger and bigger. But then the terms without absolute values cannot converge to 0 either, right? Because if the terms without absolute values were to converge to 0, then so would the terms with absolute values, but we know that doesn't happen. Okay, so the terms without absolute values don't converge to 0. So the divergence test tells us then that this series without absolute values must diverge. Okay, so here's a summary of what we've learned. This is called the ratio test. We look at the limit of the absolute values of these ratios of the n plus 1 term over the n term and call that limit r. If r is less than 1, then this series without absolute values converges. If r is bigger than 1, then this series without absolute values diverges. And we didn't talk about this, but it is important that if r is equal to 1, this limit is equal to 1, then we cannot draw any conclusions from the ratio test. Okay, so let's look at our first example. This is the example that we said we did not know how to do. So let's try the ratio test, which means we need to look at this limit. So go ahead and pause the video and try to write down what this limit is going to look like. Okay, here we go. This is the n plus 1 term here. And when we divide by the n term, we multiply by its reciprocal. So there's the reciprocal. And notice that I've dropped the absolute values because everything here is positive, right? N is positive, so n squared is positive, and so on. Now we can do a little simplification here. These 2's, there will be some cancellation. There's n factors of 2 in the numerator, n plus 1 in the denominator. And so when we cancel, there's only going to be 1 2 left in the denominator. Now that 2 is a constant, so it can come outside of the limit. And of course it comes out as a 1/2 since the 2 was in the denominator. And when we look at this limit then that we have to evaluate, we've got an n plus 1 squared, which we can multiply out. And you'll notice I've got dot 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 here, and that's because these terms are going to be smaller powers of n that aren't going to matter. Why not? Well, because this is an infinity over infinity indeterminate form, so we use L'Hopital. Right? And then we still get another infinity over infinity, and we use L'Hopital again. And when we do that, then all of the n's will be gone after we use L'Hopital twice, and we'll just have a 2 over 2, which is a 1 over 1. And when we take the limit of that constant, we just get 1. Right? So the limit is 1/2. So this is that r from the ratio test, and since that r is less than 1, the ratio test tells us that the series we started with converges. Okay, so let's do another example. We'll work with this series, and the ratio test tells us to look at this limit. And so go ahead and pause this and write down what this limit is going to be when you fill in the n plus 1 term over the n term. Okay, here's what we get. Now, I've used these rules about quotients and products of absolute values, and notice that the absolute values are gone here and here because everything's positive here. But they have to remain here and here because we've got some potential negatives after we take powers. But now I'm going to use the rule that says the powers can come outside the absolute values. And we get this. And so now we've got quite simply this -3 in absolute values here and here, which we can go ahead and evaluate as just a 3, like that. Okay, and now this problem becomes very much like the previous one when we're taking this limit. There's one more factor of 3 in the numerator than the denominator, and so the other factors will cancel out, leaving just a 3 in the numerator. That constant factor can come outside of the limit. We can multiply out this n plus 1 to the 5th, but again, the only thing that's going to matter is the n to the 5th term that'll be first in line here. We can think of using L'Hopital 5 times here. After we do 5 uses of L'Hopital, we'll get just the constant over this same constant here, coming from the repeated derivatives that we take of n to the 5th. And that constant over the same constant cancels out and is just a 1, and the limit of that constant 1 is 1. So this limit is 3. And the ratio test tells us the important thing about this limit 3, this r, is that it's bigger than 1. And so the ratio test tells us since that approximate common ratio r is bigger than 1, this series diverges. Okay, so we'll do one final example, but first we need to talk about factorials. So this n exclamation mark is read as n factorial. And n factorial just means the product of all the numbers from 1 up through n. 1 times 2 times all the numbers, and then n minus 1 times n. So for example, 4 factorial is the product of all those numbers 4 through 1, 4 times 3 times 2 times 1, and that's 24. So for us, we'll need to be able to simplify quotients involving factorials. So for example, 4 factorial over 6 factorial, both of these contain a 1 times 2 times 3 times 4 that'll cancel out, and that'll leave only a 5 times 6 in the denominator. We can think of this as just rewriting this 6 factorial as 4 factorial times 5 times 6, because again, 4 factorial is that 1 times 2 times 3 times 4, and we get the 5 times 6 will give us 6 factorial. But now 4 factorial over 4 factorial cancels out, leaving us the 1 over 5 times 6. We'll encounter situations like this, so n plus 1 factorial over n factorial. And so again, n plus 1 factorial can be rewritten as n factorial times n plus 1. Then these n factorials would cancel out, leaving us just n plus 1. Okay, so here's our final example, example 3. Let's do the ratio test on this series. And I would say go ahead and pause this video and try to do the ratio test and see what you come up with. Okay, so let's look at this limit. Here's the n plus 1 term times the reciprocal of the n term. The e's, we'll get some cancellation. After the cancellation, we'll only have one factor of e left in the numerator. And then this n plus 2 factorial, well, that's n plus 2 times n plus 1 factorial, so the n plus 1 factorials will cancel out, leaving us only an n plus 2 in the denominator. Now this limit is a limit of a constant e over a denominator that's getting bigger and bigger and bigger, and so that limit's going to be 0. What does the ratio test tell us? If this r, that's the limit, is 0, well, that r is less than 1, so it tells us that this series converges. All right, so in conclusion, use the ratio test if you've got something that may have some elements of geometric series or p-series, but it's not either one. So series that have multiplication and or division and or exponents and or factorials are great candidates for using this ratio test on.